Welcome to this explainer. Today, we're going to completely dismantle a fundamental misunderstanding about distributed systems, one that trips up even seasoned system designers. You know, if you're building or maintaining literally any system that operates across multiple servers, you've inevitably bumped into the CAP theorem. But the way it's commonly taught, it's actually deeply flawed. So today, we're going to break down the reality of how distributed systems fail, how they recover, and what trade-offs you're truly making behind the scenes.
Okay, let's dive into this infamous Pick 2 concept. Honestly, parroting this exact phrase in a system design interview is going to instantly reveal a lack of practical engineering experience. We've all seen that standard triangle diagram, right? The one where you're told to just pick any 2 points: consistency, availability, or partition tolerance. It makes it sound like you're at a buffet and can just casually load your plate with your 2 favorite features. But as we'll see, the real world of networks and physics absolutely does not work that way.
So let's lay down the rules of the game.
To figure out why that classic model is so flawed, we have to strictly define Eric Brewer's 3 properties. We need to clear away the messy colloquial definitions and look at exactly what these words mean mathematically in a distributed environment. Let's start with the C. Consistency here isn't about relational database constraints, like foreign keys or making sure a bank transfer balances a 0. It is strictly about guaranteeing that every single node in your system sees the exact same data at the exact same time. If a user writes a new value to server A and then immediately reads from server B, they absolutely must get that new value. If server B hasn't caught up yet, it has to return an error rather than hand out stale data.
Next up is the A. Availability simply means the system stays responsive and never refuses the request, even if the data it hands back to the user is a little stale. If a user asks a server for data and that server is up and running, it has to give a non-error response. It's essentially the server saying, well, I might not have the absolute latest information from my peers, but here's the best information I currently have.
And this brilliantly illustrates the final piece of the puzzle, the P. Partition tolerance means the system survives when communication lines are entirely severed. A partition isn't a server crashing, it's the network between the servers completely failing. It's a communication blackout. Think about it. If half of your servers are in a data center in New York and the other half are in London and the transatlantic cable gets cut, the servers are all still perfectly fine and alive, but they're partitioned. They just can't talk to each other.
Which brings us to the inevitability of partitions.
The harsh reality here is that across a wide area network, fiber optic cables get cut by construction crews, routers fail, network switches get misconfigured. Literally, if your system is truly distributed, it is going to experience a network partition. It is just a matter of when. To really visualize this, imagine a husband and wife running a phone reminder service. They both sit in an office with their own physical diaries. When a customer calls, whoever answers writes down the reminder and immediately tells the other spouse to write it down too. Their diaries are perfectly consistent, but one day they have a massive argument and completely stop speaking to each other. They've just experienced a network partition. Now the phone rings and a customer wants to log a new reminder. Because they aren't speaking, a choice is forced.
And this brings us to the true binary choice.
The absolutely crucial point is that you don't freely pick 2 out of 3. Because you can't magically fix a broken network in a split second, you are forced into a strict binary choice. You're already forced to have partition tolerance because the network broke. Returning to our analogy, the husband can either refuse the caller's request, telling them the service is temporarily down. He loses availability, but he ensures their diaries never get out of sync, maintaining consistency. This is a CP system. Alternatively, he can just accept the reminder, note it in his diary, and stay highly available. But he does this knowing his wife's diary won't have the update, meaning they are now completely inconsistent. And that right there is an AP system.
So what does this look like in the software we use every day? Well, if you're building a payment platform, you must choose CP. When the network hiccups, you'd much rather decline a transaction than accidentally double charge a customer, right? Consistency is totally non-negotiable. But if you're building an e-commerce shopping cart or a social media feed, you want a friction-free AP system. If a user likes a post during a network partition, you just accept the like to keep the app feeling fast and available, and you just let the databases eventually become consistent later when the network heals.
Enter the Pacey-LC theorem.
But wait, what happens when the husband and wife are getting along perfectly and the network cables are completely intact? You see, the CAP theorem only tells us what to do during a catastrophic network failure. What about the other 99% of the time when everything is actually working? This brings us to the Passel-C theorem, which is a vital extension that explains the trade-offs we have to make when our network is running normally, without any partitions. It essentially states, if there is a partition, choose between availability and consistency. Else, meaning during normal operations, you must choose between latency and consistency. So under normal conditions, you still have a trade-off. You either wait for the husband to walk over and verify his diary entry with his wife before confirming the booking with the customer, which prioritizes consistency over speed, resulting in higher latency, or you log it instantly while the customer is on the phone and sync with the wife later, trading strict consistency for lightning-fast, low latency. The takeaway here? Even when the network is perfectly healthy, you literally cannot escape system design trade-offs.
Now let's talk about the Google spanner illusion. You might hear whispers in the tech world that Google's globally distributed database, Spanner, somehow miraculously broke the CAP theorem to give us CA guarantees. People claim it provides both perfect consistency and perfect availability across the globe, completely defying the theoretical constraints we just talked about. Yet even Eric Brewer himself, the actual creator of the CAP theorem, who works at Google, clarified in a Google Cloud blog that partitions remain entirely inevitable across wide geographic areas. You simply cannot break the theoretical limits of distributed computing. If a fiber cable between data centers gets destroyed, Spanner has to make the exact same harsh choices as any other database out there.
So how exactly does Google pull off this almost magical uptime? The secret is that Google uses a highly proprietary, private global network along with specialized true-time atomic clocks. They aren't relying on the public internet to connect their servers. Because of this massive infrastructure investment, network failures contribute to less than 10% of Spanner's already incredibly rare outages.
By investing absolutely heavily in hardware redundancy, Google effectively lowered the chances of a network partition to near zero. They didn't rewrite the laws of computer science, right? They just engineered the hardware so meticulously that partitions almost never happen. This grants developers the practical illusion of a system that's both highly available and strongly consistent, simply because the trigger condition for the CAP theorem, the partition itself, is kept at bay.
Spanner basically proves that while we can never truly bypass the mathematics of network failure, we can certainly use specialized hardware to engineer our way out of the problem. It completely reframes the conversation from theoretical limitations to practical engineering budgets. Which leaves us wondering, as cloud infrastructure becomes even more advanced, what hardware innovations will redefine the practical limits of our software next? It's definitely something to think about the next time you're designing a distributed system. Thanks for joining me on this explainer, and keep questioning those foundational myths.